Okay, topics. What do you want to cover? Exam 3 review. Please. Questions, topics.
Delta age of reaction versus delta age of formation.
Okay.
That's a good question.
Which one?
It's a good question.
Okay, thank you.
Okay. Yes.
Should we go over reference states?
Reference states, good one. Okay, what else? Well, maybe we'll have some questions as time goes on. Excuse me. Okay, so
Actually,
if
yes, I have one more question.
Yeah.
So the CP values that you get in the textbook. So it gives you the equations of CP equal to A plus B times T.
yes,
So the values that you grab from like the A, B, C, and D, those are all like 10 to the power, like it's like 10 to the 30, but then the equation is just 10 to the negative 30, for example.
yes.
Why is
Yeah,
that?
so what it's just it's a fun, annoying way that they decided to tabulate this data. So if you have a table, like in the case of the heat capacity, we have C sub P is A times 10 to the 3, B times 10 to the 5?
Yes.
Whatever the case is. That means that this number x is equal to x times 10 to the minus 3. So it's saying that the number in the table has been multiplied by 10 to the 3. So you can kind of think of it as like the units of it.
Well, it's lame,
But that's how they all do it. And hopefully you guys should have all been doing that because we've been doing this for several weeks. But yeah, that's for some reason that's the system that they decided makes the most sense. Right, but you could also kind of think of this as well too, because A has units of kilojoules per mole Kelvin, but you could also think of A as in units of joules per mole Kelvin, in which case you wouldn't have the 10 to the minus 3. Right, so you can kind of think of it as like they're just presenting the coefficients in different units than how you want to unpack them. Now the reasoning behind this is that I don't know about you, but I don't want to read 0.0000572, right? It's like a lot easier just to see one or two numbers past the decimal point. So, exam 3 content. If in doubt, if you are panicked, I want everyone to write the equation here on the board. du dt is equal to the summation of the enthalpy in minus the summation of the enthalpy out plus heat minus work. If you write this down on every problem, you will not get a 0 on the exam. The key thing that I want everyone to walk away from on this class is that the problems that you are given are intentionally tedious and difficult. The reason for that is I want everyone to submit their will to the systems that we have talked about in class. All right? So that includes energy balance, mass balance, extent of reaction, atom balance. Now, not all of those are going to necessarily be on this exam in a lot of detail, but don't muddle your way through the problems. Every single problem can be solved with an energy balance, and a material balance, or a mole balance, or an atom balance. So if you are not doing one of those types of problems, or for Ralph's law, for example, if you are not starting all of your problems with either an energy balance or a mass balance, you are probably starting it wrong. Don't trust your old instincts. You might think, oh, this problem sounds relatively easy, so I'm just going to try and figure it out. No. Stick to the system. This is the energy balance. This is tabulating all of the energy in and out of the system. And that's what we worry about. That's what we care about. Now the temperature inserts itself into the enthalpy and internal energy terms. Don't just try and fiddle around. Please focus on starting off the problem in one of these very methodical ways. So virtually every problem that we're going to be doing, we'll start with this equation here. So let's do some simplifications. Let's say we have a closed system. What terms go away?
Closed system, there'd be no heat added to the system.
Yes.
Q and W?
Q and W will stay. What goes away? In a closed system.
du dt.
No, that stays.
Mass.
There is no flow in and out, so N in and N out. That's the definition of a closed system. No mass in, no mass out. So our energy balance is du dt is equal to Q plus W. Actually, no, sorry, minus W. Keep it consistent. All right? That is our system. So, this right here is not something we've typically seen. So in thermo, it's very nice. The thermo calculus is the most fun calculus you'll ever have. We want to integrate this from some state 1 to some state 2. This could be temperature, pressure, it could be time. So whatever we're saying is that since this is thermo, we don't have to worry about how we got there. We just need to go from point A to point B. So when I integrate du dt, I get u2 minus u1 because it doesn't matter how we started, how we got from 1 to 2. It just matters that we're in between those 2 points, right? So temperature and pressure. If I go from 25 degrees C to 100 degrees C, 100 degrees C is 100 degrees C. Same exact way is where, 1 kilojoule per mole for enthalpy is the same as 1 kilojoule per mole for enthalpy. This is equal to delta U. We integrate the rate of heat going into the system, and we get a total amount of heat going into the system, no dot. Same thing with work. We get a total amount of work leaving the system. And this is typically what we would see as a closed system energy balance. Now, how we would relate this to a way that we want to solve a problem is based on the definition of C sub V. C sub V is defined as du dt at constant V. So if we want to figure out how to integrate this term into something that's related to temperature, we could say here that delta U is equal to the integral of C sub V dt, or if we assume a constant heat capacity, C sub V delta T. And then our open system energy balance, C sub V delta T is equal to Q minus W. Now, the only other circumstance that we would see something different changing in the closed system balance is that if we move the work to the other side of the equation, and we say that work is equal to minus PV, P delta V. Let's see, did I get my unit convention right to do this? So if I move that over, no, I should have this plus. Because if we substitute. So to derive enthalpy, sorry, we have to say that delta U is equal to Q plus W, which is equal to Q minus P delta V. Move it to the other side. Q is equal to delta U plus P delta V, which is equal to delta H. So in this circumstance here, we have work is equal to the PV expansion. So this would be a piston cylinder device where the piston would move up and down. So we would be heating this at a constant pressure as opposed to a constant volume, and that's why it transforms out of delta U into delta H. So it's not necessarily the best way to think about the problem, saying if it's a closed system, it's always delta U. If it's an open system, it's delta H. But both the conclusions can be reached by starting off with our general balance equation. Any questions on this? We talked about this a bit throughout the class. Yeah?
So that second one is for a closed system.
It's a closed system, but operating at constant pressure. So if the system boundary can move, then it's more convenient to solve the problem with enthalpy than it is with internal energy.
Can you still have work equals PV, P delta V is assuming, like, does that take into account that it's a closed system?
So we could have P delta V on an open system here as well. But you would have to have an open system with a moving boundary. So for example, like a balloon with a feed in and a feed out, and if the feed in is higher than the feed out, it'll expand a little bit. You could still have PV expansion work in an open system, but it's difficult to design. So it's not typically something we see. So usually in an open system, this work here will be shaft work. So it'll be like a pump blade spinning or a turbine sucking the energy out of the process. In a closed system, we always like the frictionless piston cylinder device. Okay, so this is closed systems. Now, for a ideal gas, C sub P is equal to C sub V plus R. Or the other way you can think about this is that, let's see, H is equal to U plus PV. And for an ideal gas, this is U plus RT, right? PV is equal to RT. If I differentiate both sides with respect to temperature, we get dH dt is equal to du dt plus R, which is also equal to C sub P is equal to C sub V plus R. This is for an ideal gas. For a liquid, C sub P is approximately equal to C sub V, because this PV contribution is very, very small for a liquid or a solid, for a liquid and a solid. Right? Pressure doesn't really affect the properties too much of liquids and solids, so we don't have to worry about it. Unless, of course, we're going to extremely high pressure conditions, in which case we've talked about integrating the PV, or saying V delta P, for example, if we assume it's a constant density of the system. Is all this ringing a bell? Good. Okay. Open system. If I'm going to simplify this equation right here, is there anything that I can immediately get rid of that's an open system?
Is it du dt?
So we've generally assumed that we get rid of du, but this equation, nothing can be immediately gotten rid of if it's an open system, because this is the general energy balance equation for an open system. But we've typically assumed it's steady state. Open system and steady state, then we get 0 is equal to the summation in minus the summation out plus Q minus W. And this is something we've applied a lot of in the class. So, the difficult part, I'll write the N and H here. Now, all the attention that most of the time we've spent is focusing on these enthalpy values. And that's what all the questions are that we have over there. Delta H of reaction versus formation, and reference states. So, how do we get enthalpy? The number one best way is to look it up. Someone has measured this for a lot of different materials. For the steam tables, that makes things very easy. When we look something up, you'll notice that there's a reference state. So for the steam tables, U at 0.01 degrees C as a liquid is equal to 0 kilojoules per kilogram. If you go in your book, hopefully you'll find that entry in the table. So at a temperature just above when water freezes as a liquid, we say that water has no energy. Absolutely zero energy. Strictly speaking, we do not have an accurate, unbiased way to know the total amount of energy contained within any single compound. And if that were the case, it's not exactly clear what energy we even care about. Is it the energy of the bonds of the valence electrons? Is it the energy of the bonds of the core electrons? Is it the energy that's stored in the nucleus, that if you had it decompose in a nuclear reactor? Right? What energy do we really care about? So there's so much energy contained within these systems that doesn't matter. It goes through the process entirely. Right? So I don't exactly know how much energy is in it, how much material is in an atomic bomb, but it's probably on the order of like grams to kilograms of radioactive material. And that releases a lot of energy when it blows up. Now imagine that we're doing energy balances on our chemical process for the formaldehyde plant, and we have thousands of kilograms per hour. Now, if we had to keep track of all of the energy stored in the nuclear process, it's just a waste of our time, right? Because there is no nuclear process in our system. All of the chemical bonds that we deal with respect to chemical reactions, those are all bonds involving the valence electrons of these molecules, nothing involving the core electrons. So why do we care how much energy it takes to rip a core electron out of a system? So the best way to handle all of the different sources of energy is just to ignore them and only focus on the processes that we care about. And that gives us reference states. So in step 2, we have to calculate it. And how we calculate the enthalpy is we calculate a series of delta H or delta U steps, depending on what type of problem you're solving, going from the reference to the final state. And by final, I mean any H hat. This could be the initial, this could be the outlet, that could be the final. So because there's so many different forms of energy, we just forget about all of them. We're just going to say at some point this has zero energy. And when we choose a reference state, we can have negative energy and negative enthalpy. That's totally fine, right? Because the math all works out that when you substitute those numbers into here, right, it doesn't matter if you're adding a negative or adding a positive or negating a negative, well, whatever the case is. Right, so that is the core reason why we have reference states. It's both a matter of practicality and a matter of inaccuracy of our ability to calculate these things very well. What we have talked about primarily is how to calculate changes in enthalpy based on different state changes of the system. Predominantly, delta H versus temperature is the one that we have focused most of our attention on. And this is going to be based on the definition of C sub P. C sub P is defined as dH dt at constant P. So all of what we're doing in thermodynamics is a roundabout cyclic logic process. We say we need the enthalpy, but in order to get the enthalpy, we need the C sub P. In order to get the C sub P, we need the enthalpy. So effectively, what we're doing in this class is all we're doing is allowing someone else to measure the enthalpy, calculate a C sub P, and then we use the C sub P to calculate new different types of problems. So that's why I always emphasize in thermo, we're not really teaching the answer, we're teaching the system. All we're doing is unpacking the data that someone else has already provided for us. So when we rearrange this expression, the delta H going from some T1 to T2 is equal to the integral from T1 to T2 of C sub P dt. Now, when we look in the back of the book, what we are looking at is tabulated data that someone has plotted and put a fit onto. So as a function of temperature, we have data points. And C sub P value should look a bit like this. The heat capacity will always increase as the temperature goes up. And this is because you're activating different modes and different ways for the molecule to store energy. So the correlations in the back of the book for Felder of C sub P are no more complicated than someone looking up calculated values of C sub P, plotting them on a graph, and doing basically what everyone's done, I'm sure, on Excel. Add regression. Okay, add polynomial regression. Okay, first order, no. Second order, no. Third order, no. Fourth order. Oh yeah, we get a good fit on the fourth order polynomial. That's it. And the reason why they chose a polynomial is because a polynomial is easy to integrate. Because why do we care about C sub p? So we can calculate delta H. That's the most important part. The truest application of the heat capacity is integrating it to solve for a delta H. If you want to simplify your calculations, you could just plug in any temperature value and read off any specific heat capacity value. But the integration process is you are calculating the area under the curve, which corresponds to the delta H going between those two temperatures. But there's absolutely no theoretical basis for why the polynomial fit is chosen. In fact, the polynomial fit is actually bad. Because in reality, if you plug it in, you'll get something that looks like this, which is bad. Because this part right here is theoretically not possible. I don't know it for sure, but it probably violates the second law of thermodynamics. Actually, I know it violates the second law of thermodynamics. So you can never have a heat capacity going down. Right? Heat capacity always has to increase as you increase the temperature. Right? But the polynomial fits, that's not that big of a deal. Sure, it violates the second law a little bit, but it makes it super convenient. But if it's a really good fit, it shouldn't. Right? It probably should be some complex exponential function, which is a lot harder to integrate. And in fact, from statistical mechanics and physical chemistry, it is sort of a complex exponential function. Okay, so this is delta H versus temperature. But the idea here is that if I need an H value, an actual number that I can plug into my actual energy balance and solve for an actual heat or an actual work, like you'll be asked for on the exam, what I'm doing is I'm saying I'm calculating the delta H of some delta T transition from state 1 to state 2. Delta means H final minus H initial. If I'm starting off and my initial state is my reference state, I can say this is 0, which means that my delta H is now equal to that enthalpy value that I plug into my table. Yes?
But you have to first, so the only time you can do that is if that's at your reference state then?
Correct.
So on like the test, for example, like would you like tell us like a reference state? Or would we have to kind of like?
So the only time, so I will never tell you the reference state.
Okay.
The table that has the heat of formation data will tell you the reference state. But for the exam, you can choose any reference state unless it's specified.
Okay.
But on the table, like if you looked at the practice exam, who's looked at the practice exam? There's a big data table at the end of it. So I don't have to give you specific information. So I'll probably do a similar format. You'll have a table, I'll probably print it separately, and you can look at it. It'll have heat capacity values, heat of formation values, molecular weights, densities, whatever information you'll need, right? So that we can actually solve real balances and not A plus B goes to C type thing. So that table will say the reference state. This is the heat of formation at this condition, in which case you're stuck, because then you have to start from that point onwards, because it's the only place where you have the data. But if we're doing an energy balance on a flash separator, you get to choose the reference state. It could be arbitrary, or it could be one of the process flow streams to make your energy balance more straightforward. But let's say in the case that we have, I'm going to say my H hat ref is equal to 0 at, let's use the water condition, 0.01 degrees C as a liquid. And I need to calculate the H hat of vapor at 120 degrees Celsius, let's say. Let's just say, for example, I'm cooling down steam and I want to see how much energy I can pull out of it in a turbine or an expander. In this circumstance here, I can't directly go from my reference state to my final conditions, but I can break it up into smaller steps. So I ultimately am going from my reference state to my final conditions. So what I'm going to say is I want delta H, it's going to be a series of delta H's here, is ultimately going to be equal to H hat, I'm just going to call this final, H hat final, minus my reference. This is going to be 0. So if I can calculate a series of delta H's that take me from my reference state to my final condition, I will have that number.
So then for this example, it would just be, you just take it up to 100 degrees. So you'll do like a CP from 0 to 100.
Lots of possibilities, because if this is actually water, I could look up a lot of different ways to do it. I could vaporize this cold water and then heat the vapor, or I could heat the liquid, then vaporize, then heat the vapor, which is what I'll demonstrate here. So we could say delta H of the liquid going from 0 to 100 plus delta H of vaporization, these are all specific ones, so they're hats on them, at T equals 100 plus delta H going from 100 of the vapor to 120. Right? So these are all the steps that I've taken. So I've gone from the reference state to my final condition in 3 different steps and pathways. So this one would just be integrating C sub P of the liquid. This would be vaporizing it by looking up the value. And this would be heating up the vapor by integrating the heat capacity of the vapor. But the core concept here is that I'm going from my reference state to my final conditions. And this is just as how, like for example, a TXY diagram has every flash calculation built into it, right? So if you have a TXY diagram for a binary mixture, you can solve any combination of flash problems using that TXY diagram. Any feed in, any temperature in, any conditions at all. The steam tables have done this process here for every temperature and pressure combination, every phase combination that exists. So that's why the steam tables are so useful, because someone's already done all this work. But if you only need one number, then there's no point of going through the entire process of solving for the entire steam tables. Just calculate that one number that you need. Does that make sense? I know reference states are always sort of the trickiest part. What are the questions we have on reference states? What is not clear about this description? Don't feel shy.
So,
Yes. Oh.
no, I didn't raise my
Question.
I just had a question. Kind of, it's similar to this. When you're finding the heat of vaporization
Mhm.
or something, you take like the heat of vaporization, or like on the practice exam,
Mhm.
is that one. Why do you have to do the liquid cooling down part of it?
Oh, very
Do you
good
know?
question. Let's do that question. I like that. It's asking for the heat of vaporization as a function of temperatures is one of my favorite questions to ask. So the first thing to start off with is that the heat of vaporization is something that we have to measure. We don't have an innate way to just spontaneously know what the heat of vaporization is for any particular compound. So, if we were to look at a phase diagram, a PT diagram, this curve right here is the vapor pressure. Here is our critical point. So above the critical point, we have no heat of vaporization. At high pressure and low temperature, we have a liquid. At high temperature, we have a vapor. So the way we want to think about this curve is that imagine we have a third axis coming out of the board. That is our enthalpy. What the heat of vaporization is how tall that cliff is. Right, so let's say the liquid here, right, so this is basically, we're kind of looking at sort of a contour or like a topographical map or something like that. Now the liquid is gradually sloping up as you get closer and closer to the critical point because it's got more and more energy. And the vapor is also gradually sloping up, but not as steep. So the way to think about this then is, I don't know if I can draw a very good 3D perspective on the board. But imagine this is, coming out of the board. And the heat of vaporization is estimating how tall this cliff is. Right, so let's say we're doing the opposite. Let's say we have a rope of a particular length. Right, and then we want to go down from the vapor enthalpy to the liquid enthalpy. But we only know how long the rope, how tall this cliff is at one position. And so that's the position you want to know. You're like, hey, I can get down at this point in the cliff. So I'm going to use the tabulated value of the heat of vaporization because I know that I can get from the vapor to the liquid following that pathway. I know how much energy it takes, or in this silly analogy, how long, how long of a rope do you need? So in the case of, if I want to estimate up here, for example, right, I only know how tall the jump is from liquid to vapor at this one position. But if I want to get here, what I can do is I can estimate how much the elevation changes here and estimate how much the elevation changes there. And when I add the whole process together, it lets me know how tall that part of the cliff is. It's a very silly analogy. So in terms of the enthalpy, what we're doing is we're going from a saturated liquid to a saturated vapor in the heat of vaporization. But because this is thermodynamics, I can choose any arbitrary path that I want to take. So I could first calculate the enthalpy to go here, calculate the enthalpy to go here, calculate the enthalpy to go here, calculate the enthalpy here, and then calculate the enthalpy there. And so you have to complete the circuit going from a saturated liquid at one temperature to a saturated vapor at another temperature. And so if I need to estimate that along the way, what I'm effectively doing is measuring how steep each of those two slopes are and tying the whole process together, and it should add up to the right heat of vaporization. So that help clarify it?
I think so, yeah.
Perfect. Any more questions? Everyone is 100% crystal clear on references. Yes?
What's the difference between the standard heat of reaction and the heat of reaction?
Oh, okay. So that would just be at the conditions where it was measured at. That would be the equivalent of saying this is the heat of vaporization at the normal boiling point versus the heat of vaporization at some other point.
Okay.
So in the homework, you had a problem, I think, where it was talking about, making toluene out of heptane, where you did it at standard conditions of 25 degrees C, you calculated the delta H, and then you had to repeat the calculation, but isothermally at 400 degrees C. And then that would be the heat of reaction at 400 degrees C. So in the case of this circumstance here, when we go from here to here through, let's say, the normal heat of vaporization, we heat the liquid, vaporize it, and then we cool the vapor back down. In the case of the heat of reaction, if I have some A plus B going to C plus D, at 25 degrees C, this is the delta H of reaction at the standard or the reference state at 25 degrees C. But if I wanted to estimate the heat of reaction at some T hot, I would not put the little standard state symbol there. But all I would be doing is imagine that I basically heated the reactants, heated the products, and the imbalance of the heat capacity in A and B and the heat capacity of C and D means that this changes as a function of temperature. So if it takes exactly the same amount of energy to heat up A and B as it does to heat up C and D, your heat of reaction is not a function of temperature. And this is a topic that will be very heavily covered in the reactor design class. But if you're taking material, right, that has a low heat capacity and you're forming something that has a high heat capacity, maybe something that's really heavily associating, right? So this would be more so the case maybe as a liquid phase reaction as a gas phase. But that's a circumstance there where the heat of reaction would be a strong function of temperature. But that's the difference, is same general concept as the vaporization example, whereas in this one here, it's just the reactants and products, how much energy it takes, as opposed to here, where it's how much energy does it take to heat a liquid versus how much energy does it take to heat a vapor. Same concept. Okay, so there's no more questions. Let's go on to the reacting systems. So I think that's the only other concept that we really wanted to talk about. All right. So let's say we have a reacting system. The energy balance doesn't change. And the Felderbrook tries to overcomplicate it a little bit. reacting system, non-reacting system, this is always going to be the same material balance. Or sorry, same energy balance. For heat of formation, it's a very straightforward application. For heat of reaction approach, they manipulate it a little bit. But let's just say, for example, we don't have any phase changes going on. No phase changes. So that means every enthalpy value is going to be equal to forming that compound plus some additional delta H step. I'll call it delta H question mark. Whatever needs to happen, right? That could be heating it, it could be cooling it, it could be vaporizing it, it could be pressurizing it, right? So this could be any series of delta H steps, just like what we talked about over here. Whatever you need to do to get from the reference state to whatever the final conditions are, that's all you need to worry about. So when we consider all the stuff coming in and all the stuff coming out, what we can do is if we take this heat of formation and we pull it out of every single one of these enthalpy terms, that gives us the heat of reaction at the standard state effectively. So if we say that this is equal to 0, we say that this is equal to 0, typically when we're doing a reacting system, we're not going to be trying to overcomplicate it by also having some sort of expanding pump going on, but maybe you could have a scenario where that's the case. So Q is then equal to out minus in, because we move everything over to the other side of the equation, summation of n dot h hat out minus summation n dot h hat in. So if we plug in these expressions here, we have h is equal to the summation of n dot times by delta h of formation plus some delta h question mark. That's out. Minus summation of n dot delta h of formation plus delta h question mark in. So then if I pull out, or rather I distribute this sort of n dot throughout the whole process, I can rewrite this expression then as summation of n dot delta h formation not of everything coming out minus the summation of n dot delta h of formation of everything coming in plus the summation of n dot delta h question mark out minus summation n dot delta h question mark in. So slightly different notation than I've used previously. But this expression here, out minus in, is effectively just the heat of reaction for this process. Yes?
That would be the heat of reaction times the extent of reaction.
Yeah, I was just thinking about, I'm kind of pulling this one off the top of my head. So let's see, we have n out is equal to n in plus the stoichiometric coefficient times by the extent of reaction. So let's see if we can merge these two together to make it all nice and kosher. Let's see. So if we n out minus n in is equal to mu I, so n out minus n in is equal to the stoichiometric coefficient times by the extent of reaction, which is the form we're trying to get it into. Let's see. So we have this for every species in the system. So we can put these together. Let me think about this. Out minus n. Yeah, this is getting a little bit funny math. It will all work out. It just all depends on how we want to write this as a notation. Out minus n. So if this is the same species I, right? For every I species, n dot delta H formation out minus n dot delta H formation in, we could equal this to be n dot out minus n dot in is equal to delta H of formation, which would then be equal to nu I stoichiometric coefficient delta H of formation. Then if we sum this up, we would get stoichiometric, so we sum this whole process up, sum it up, and we would get this is equal to summation of nu I delta H of formation, which is equal to extended reaction delta H of reaction. All right, so hopefully you guys follow that.
So just to clarify then, so your delta H of formations of your stuff leaving minus the delta H of formations of your stuff going in that is equal to your delta H of reaction.
Yeah, so these terms put together here, this term here is equal to the extent of reaction times by the delta H of reaction at the standard state.
So if you were to ask us for like the delta H of reaction for like our problem, you could just look at the delta H of formations and that would be sufficient.
Yeah, that's the only way we know how to calculate it actually. Either you measure it and you look it up, or if you calculate it, this is equal to the summation of stoichiometric coefficient delta H of formation. So let's just go over really quickly this math over here. So we're trying to get this to look like what we've seen in the delta H of reaction approach, which is, so in the case of the delta H of reaction approach, Q is equal to the extent of reaction, delta H of reaction at standard state, plus the summation n dot H hat out minus summation n dot H in. Right? This is the material. This is the energy balance that we've used for the the reaction approach. So we started off here with what we're saying is the heat of formation approach's energy balance. And if we substitute in our formula for the enthalpy based on forming it and going through whatever series of steps we have to go from the reference state to the final state, right, we can break it down here where we have all of the out minus all of the in. We can grab the heat of formation terms, plug them into this equation, and then up here in this corner is where we sort of started going off the rails a little bit. This is our definition of the extent of reaction. Out is equal to in plus how much changes. The stoichiometric coefficient times by the extent. We rearrange this. Out minus in is equal to stoichiometric coefficient times by the extent of reaction. We take our term that was right here. We manipulate it for every species I. Out minus in. So we're actually only considering what actually reacts. Because in this case here, we're considering everything. If it reacts, if it doesn't react, whatever the case is. But by pulling it out this way, we're only looking at what the difference is of how much it reacts. Then we can substitute in our extent of reaction definition. We resubstitute it back into here by summing it all up, and we get the difficult to draw extent of reaction times by the delta H of reaction. So they're the same. I'm just trying to demonstrate that they're the same concept. We're all starting off with the same energy balance, but it just depends on how you want to organize everything. Yes?
I remember there was one question in the homework, I don't have it exactly, but it was asking for us to find the enthalpy of a single species at some conditions using heat of reaction. We didn't have any sort of reaction. So in that case, would that first extent term, that would just be the single heat of formation of the one species? And then basically
So in that case, you would basically, so that goes back to what we're calling the reference states. So in both of these approaches, I need a number that I can put for my enthalpy out, and I need a number that I can put for my enthalpy in. If I'm using the heat of formation approach, this is my strategy. I first create the molecule out of nothing, or just rather the atomic constituents, and then I manipulate the phase, the pressure, the temperature to get whatever conditions I need to get to. In the heat of reaction approach, we have a different reference state. So in delta H of formation method, our reference is 25 degrees C, 1 bar, and atomic species, right? Meaning that I have to first create the molecule before I can heat it up. In the delta H of reaction approach, my reference state is 25 degrees C, 1 bar, and the molecular. So by doing this algebraic manipulation that we demonstrated here, we're grabbing this term out of my enthalpy value, and I'm putting it into this heat of reaction. So I'm physically modifying the number that I put into my summation. So when I build a table to solve my problem of all the enthalpies in and all the enthalpies out, the number that I put into that table will change. But the overall energy balance will stay the same. I'm just sort of reorganizing how I think about the problem. Does that help clarify the question?
Thanks. So this, if you just have one species, the formation of that species goes into the first term, and then your out and in is bringing the full molecule to whatever
Yes.
conditions.
Correct, yeah. So this term here, I will take it out of the H value that I put into the table, that actual number that I calculate to put into this actual summation. Right? I'm taking that term out, so I'm pulling it away from every single one of those H terms, and I'm putting it into the heat of reaction. And so it's just how I'm organizing the calculation a bit differently. But how it manifests in terms of the reference states is you can think of it that at the heat of formation, your reference state is atomic species, and you first have to create the molecule, which is the delta H of formation, whereas in the reaction step, you already have the molecule, you just need to manipulate its temperature and pressure to get whatever the conditions that you want are. Yes?
Sorry, this might be a stupid question, but so that delta H of reaction still, though, is equivalent to the sum of all your outs and ins for delta H.
Effectively, so how we calculate delta H of reaction is the summation of the stoichiometric coefficients times by the heats of formation. So this is how we calculate the heat of reaction. This term here looks a little bit different because we're adding in the extent of reaction. So the heat of reaction is only based on the equation that we draw, right? Am I burning 1 mole of methane, 2 moles of methane, 10 moles of methane? Am I having 5 halves oxygen or 5 oxygen? Right? So how I write the equation changes how I get my stoichiometric coefficients, which will change my heat of reaction. But it doesn't matter how you write the equation as long as it's balanced, because your extent of reaction will change based on how much reacts and how you've written the reaction. So that's why we need to include that extent of reaction here, because the heat of reaction is just a thermodynamic calculation. It tells us nothing about how much actually reacted, and that's why we need that extent term there. That's it. All right, so I have office hours. So there's office hours today with Caitlin. I have office hours tomorrow, and then the exam on Friday. All right, see ya.
Professor